students, welcome to Sunil's tutorial. I am Sunil Midwani and today we will be doing this chapter called as semiconductor. Now, let us try to understand what is energy bands. Let's try to understand the concept of energy bands. What are energy bands? Now, in the case of solids, the atoms are arranged in symmetrical space of crystal lattice. They are closely packed and arranged, right? Now, they are greatly influenced by, or they are closely packed in a very small volume, and hence every atom is greatly influenced by a neighboring atom. Since they are so close to each other, every atom is greatly influenced by a neighboring atom. Now, the energy level of an individual atom is formed due to the interaction of positive charge in the nucleus and the negative charge in the electron. We've already learned this in Bohr's atomic theory. What is the energy possessed by the atom depends upon the positive and the negative charge, the interaction of positive and negative charge. Now, in the case of solids, the electrons in some orbit are under the influence of large number of positively charged nuclei from the neighboring atom. Since the atoms are closely packed, the electrons are under the influence of the neighboring atom. The electrons in some orbit of an atom are in the influence of the neighboring atom, right? Now, depending upon the influence depends upon what is the distance of the neighboring atom from the given atom, right? Now, this effect is more pronounced in the case of valency shell electrons. The valency shell electrons experience strong forces from neighboring atom, right? Now, this is in the case of those atoms where the atoms are closely packed to each other. Now, in the case of some atoms, in the case of some substances, the atoms are not closely packed to each other. Hence, the valency shell electrons do not experience forces from the neighboring atom. Hence, the total energy possessed by an atom, right? The total energy possessed by an atom significantly changes due to the interaction forces of the neighboring atom. Had it been just the atom and the electron, it would have had some energy level. But due to the interaction of forces of neighboring atom, the energy level possessed by an atom is greatly changed, right? This that means here, instead of having a single energy, had there been only an atom and electron, there would have been only a single energy that would have been possessed by every orbit of the electron. But here, due to the forces of the adjoining atom, there are more energies. There is a band of energies that is possessed by every orbit, right? And these are called as energy bands, right? So, see, if you had nucleus, you have first orbit, second orbit, third orbit at a distance of say R1, R2 and R3, right? Ideally, had there been only one atom and the electrons in it, at a distance of R1 there would have been some energy level which would be called as a first energy level. Then there would have been, at a distance of R2, there would have been a second energy level, and at a distance of R3, there would have been a third energy level. But this is not going to be there. This is only in the case of an isolated atom. In a crystal lattice, due to the interacting forces of the adjoining atom, instead of having energy levels, you are going to have energy bands. You are going to have, instead of just a single energy, due to the interacting forces, there are going to be a range of energies that are going to be present at a distance of R1. This will be called as the first band. This will be called as the second band. and similarly this would be called as the third band. So there would be, instead of having a single energy level, you would have a band of energies. Do you understand why you would have a band of energy? Due to the interacting forces of the adjoining atom. Due to the interacting forces of the adjoining atom, instead of having a single energy, you would have a band of energies. Fine, do you get this thing here? Okay, now let's see, what do you understand by energy band? What do we understand by energy band? Right? Now, energy band, the range of energies possessed by an electron in a solid is known as the energy band. The range of energies possessed, the range of energies possessed by an electron in an atom, in a solid, is known as energy band. Right? So it is known as energy band, or in the case of solids, instead of having a single energy level, the energy level associated with a single atom, when there is an energy level associated with single atom, there will be a band of energies, and these closely packed energy levels is called as energy bands. I think this is a better definition, and the range of energies possessed by an electron in a solid is known as energy band. The other definition would be, in case of solids, instead of a single energy level associated with a single atom, there will be a band of energy levels, and such closely band of energy levels would be called as energy bands. Fine, do you understand this? Now, question, why do I need to understand energy bands? Now, first of all, let's understand what is valency band. What do we understand by valency band? Now, the electrons in the outermost shell are not strongly bonded to the nuclei. Why? Because they are at a very far away distance from the nucleus. Now, these electrons which are in the outermost shell are called as valency electrons. Now, the range of energies possessed by valency electrons is called as valency band. The valency electrons, the electrons in the outermost shell, would have a band of energies. Why would they have a band of energy? Because of interacting forces of the adjoining atom. Right? And this band of energies is called as your valency band. Fine, do we get this thing here? So I can say that the electrons in the outermost shell, electrons in outermost shell are not strongly bounded, to their nuclei. Are not strongly bounded to the nucleus. These electrons are called as valency electrons. These electrons are called as valency electrons, right? And the range of energies possessed by valency electrons is known as valency band. The range of energies possessed by valency electrons is known as valency band. Fine, do we understand what is valency band? Next. Now, in a normal atom, the valency band has electrons in the highest energy. Hence, the valency band can also be defined as a band that has highest, or which is the highest occupied energy band. Right? The band may be completely or partially filled depending upon what kind of material or substance are you taking. Right? So that is your valency band. Next. you have something called as conduction band. Now, so long as the electrons are there in the valency band, there is going to be some influence of the nucleus on those electrons, right? And hence they will not be free electrons. For a substance to be a conductor, I need free electrons. That means I need those electrons which are not under the influence of the nucleus. I need those electrons which are not under the influence of nucleus. There are some electrons which have acquired sufficient energy. There are some electrons in the valency orbit which have acquired sufficient energy and have are no longer under the influence of the nucleus. All such electrons are present in a band of energies which is called as conduction band. So it is that band which contains all free electrons. It is the band of energies that contains free electrons. Fine, do we get this thing clear? So even at ordinary temperature, valency electrons may get detached from the valency band. These electrons which are detached or which are not there in the valency orbit, these electrons which are detached from the valency band are called as free electrons, right? These electrons are responsible for conduction of a substance. These electrons are also called as conduction electrons. So the range of energies possessed by conduction band electrons is known as conduction band. Fine, do we get this thing clear? I can say that in certain materials, valency electrons are loosely attached to the nucleus. Even at ordinary room temperature. Even at ordinary temperature, some of the valency electrons may get detached. Some of the valency electrons may get detached. Some of the valency electrons may get detached from valency band. Right? These electrons are called as free electrons. These electrons are called as free electrons. Right? Now these electrons are responsible for conduction of current in a conductor and hence are also called as conduction electrons. These electrons are also responsible for conduction of current in a conductor and hence are also known as free conduction electron and hence are also called as conduction electrons. Fine, do you get this in clear? So now the range of energies possessed by the conduction electrons is known as conduction band. The range of energies possessed by conduction electrons, the range of energies possessed by conduction electrons is known as conduction band. Fine. This band is always next to the valency band, right? So the conduction band may also be defined as the lowest unfilled energy band. This band is next to valency band. This band is next to valency band. So I can say that the conduction band may also be defined as the conduction band may also be defined as the lowest unfilled energy band. The lowest unfilled energy band. Fine. So do you understand what is conduction band? Next. Now see, the valency band possesses some energy. Electrons which are there in the valency band are bound to the nucleus. The conduction band contains those electrons which are free electrons. They are not bound to any nucleus. That means these electrons, these valency electrons must have acquired some energy. That's the reason why they are in the conduction band. That means there has to be some energy difference. There has to be some energy difference between the electrons which are there in the valency band and which are there in the conduction band. This difference between the energy levels of the valency band and the conduction band is called as the forbidden energy gap. Okay. So what is the forbidden energy gap? It is the separation between the conduction band and the valency band. Right? It is the separation between the conduction band and the valency band. That is called as your forbidden energy gap. Fine? Let's write this down. Forbidden energy gap. Forbidden energy gap. The separation between conduction band, and valency band is known as forbidden energy gap. Fine. So do you understand what is forbidden energy gap? There is no allowed energy state in this gap. Hence, there are no electrons that can stay in the forbidden energy gap. Right? The width of the forbidden energy gap is a measure of the bondage of the valency electrons. If the valency electrons are closely bound to the nucleus, then the forbidden energy gap will be bigger. If the valency electrons are loosely bound to the nucleus, then the forbidden energy gap will be smaller. Right? So that means the greater the energy gap, the more tightly is the valency electron bound to the nucleus. Right? In order to push an electron from valency band to conduction band, some external energy which is equivalent to the forbidden energy gap has to be supplied. Right? Now that we know what are the different energy bands, let's try to classify elements. What are insulators? How do I define insulators? This is my valency band. Valency band, and this is my conduction band. Now, in the case of insulator, the forbidden energy gap, this is my forbidden energy gap. It is nothing but the difference between the energy levels of the conduction band and the valency band. right? Gap. Now, the forbidden energy gap in the case of insulators is very large, right? Which is of the order of say 15 electron volts. This energy gap is of the order of 15 electron volts, right? This is my band energy on y-axis. Right? So, do we understand this? Here, the forbidden energy gap is very large. Hence, an electron on its own can definitely not jump from the valency band to the conduction band. Even when external heat is supplied, a large amount of external heat would be, you would have to supply a large amount of external heat to push an electron from the valency band to the conduction band. Fine, do you understand this? So what are insulators? Insulators are those substances which do not allow the flow of electric current in them, right? In terms of energy band, their valency band is completely filled at 0 degree Kelvin, while their conduction band is completely empty at 0 degree Kelvin. Since their conduction band is completely empty, they do not have any free electrons. And since they do not have any free electrons, they obviously cannot conduct any current, right? Moreover, the forbidden energy gap between the valency band and the conduction band is very large. Hence, even at ordinary room temperature, in the presence of high electric field, I am not able to push an electron from the valency band to the conduction band. Very large energy would be required, fine, to push an electron from the valency band to the conduction band. Hence, at room temperature, the valency electrons of the insulators do not have sufficient energy to jump and cross over to the conduction band, right? Increase in temperature enables very few valency band electrons to go into the conduction band. This is the reason why insulators do not conduct electricity at room temperature. They do not have any free electrons, therefore they will not conduct electricity. For a substance to conduct electricity, they should have free electrons. Fine, do we get this thing here? So I can say that in insulators, the energy band, in insulators, the valency band is completely filled. The valency band is completely filled at 0 degree Kelvin, while the conduction band is empty, right? The energy gap between the valency band and conduction band is very large. The energy gap between the valency band and conduction band is very large, right? Now, hence, in the presence of high electric field at ordinary room temperature, the electrons do not move from the valency band to conduction band. Hence, in the presence of high electric field, hence in the presence of high electric field at ordinary room temperature, electrons do not move from the valency band to the conduction band. Electrons do not move from valency band to conduction band. Electrons do not move from valency band to conduction band, right? Now, so the valency electrons in the insulators do not have enough energy to cross over to the conduction band, right? So I can say that, therefore I can say that at room temperature, valency electrons do not have enough energy at room temperature. Valency electrons do not have enough energy to cross over to conduction band, they do not have enough energy to cross over to conduction band. Increase in temperature enables some valency electrons to go into the conduction band. Increase in temperature enables some electrons to go to conduction band. Right? This explains why certain materials are insulators at room temperature and become conductors at very high temperature. Right? Because at very high temperatures, these substances acquire, the electrons in these substances acquire sufficient energy to jump from the valency band to the conduction band. Fine, do we get this in clear? The resistivity of these substances is extremely high. It is of the order of 10 to the power of 7 or 10 to the power of 11 ohm meter. Right? Their resistivity decreases with temperature. Obviously, as the temperature increases, more and more electrons would acquire sufficient energy to jump from the valency band to the conduction band, and therefore their resistivity would decrease. Right? Next, let us see what are conductors. In the case of conductors, there is no forbidden energy gap. The valency band and the conduction band overlap each other. The valency band and the conduction band overlap each other. This is my valency band. This is my conduction band, and this is the overlapping of them. They overlap each other here. Valency band this is conduction band. Right? So in the case of conductors, these are those substances in which current flows very freely. Now why does the current flow freely in them? This is my band energy. Why does current flow freely in them? This is the band energy. Right? Current flows freely in them. Because the valency band and the conduction bands overlap each other at 0 degree Kelvin, right? Hence, electrons from valency band can freely enter into the conduction band, as a result of which there are large number of free electrons which are present in the conduction band, and since there are large number of free electrons present in the conduction band, even a small potential difference is sufficient to cause these free electrons to constitute electric current. Fine, do you get this in clear? Now, in conductors, valency band and conduction band, overlap each other at 0 degree Kelvin, right? Now, thus I can say that the electrons from the valency band can freely enter into the conduction band. Therefore, electrons from valency band can freely enter into conduction band. Electrons from valency band can freely enter into the conduction band at zero. Hence, large number of free electrons are available for electric conduction. Since there are large number of free electrons in the conduction band, I can say therefore large number of free electrons are available for conduction. Large number of free electrons are available for conduction. Large number of free electrons are available for conduction, right? Now, due to this, a slight potential difference across conductors causes these free electrons to constitute electric current. Okay? Due to this, a slight potential difference across the conductors causes free electrons to constitute electric current. Causes free electrons to constitute electric current. Right? So these are conductors. Next, let us see what are semiconductors. Now, in the case of semiconductors, the forbidden energy gap between the valency band, there's a forbidden energy gap between the valency band and the conduction band, but the forbidden energy gap between the valency band and the conduction band is extremely small. So, this is my valency band. This is conduction band. This is my forbidden energy gap. Right? Now, the forbidden energy gap is very small here, which is of the order of only 1 electron volt. Now, in the case of semiconductors, at absolute zero, that is at 0 degree Kelvin, or at extreme low temperature, all the electrons are tightly bound to the nucleus, and all the electrons are there in the valency band, right? The inner orbit of the nucleus as well as the valency electrons are all engaged in covalent bonding. Hence, at room temperature, the covalent bonds are extremely strong and there is no free electron, right? Now, the energy gap between the valency band and the conduction band is very large at 0 degree Kelvin, right? Now, so the electrons A, they are very tightly bound to the nucleus. B, the energy gap is sufficiently large, hence electrons do not possess sufficient amount of energy to jump from the valency band to the conduction band, right? As a result, at absolute zero or at 0 degree Kelvin, these substances behave like insulators, right? When the temperature increases, some of the covalent bonds break due to the thermal energy supplied. This sets the electrons free, which were engaged in the formation of these bonds. Now, the thermal energy which is capable of breaking the covalent bond gives sufficient energy to the electron so that it can jump from the valency band to the conduction band. So as a result, when the temperature increases, you have more and more electrons coming into the conduction band, right? As the number of electrons in the conduction band increases, the ability of the substance to conduct electricity also increases, right? And that is the reason why these substances behave like conductors at room temperature. Fine, do you get this thing clear? So here they would exhibit two different types of behavior. One is the behavior that they would exhibit. One is the behavior that they would exhibit at absolute zero. The other is the behavior that they would exhibit at room temperature. Fine, do we get this thing clear? So let's see this. First, I can say that at absolute zero temperature, at absolute zero temperature. Now, at absolute zero temperature, that is at 0 degree Kelvin, or at very low temperature, at 0 degree Kelvin, or at very low temperature, at 0 degree Kelvin or at very low temperature, all the electrons are tightly held by semiconductor atoms. All the electrons are tightly held by the semiconductor atom. Right? So all the electrons are tightly held by the semiconductor atom. The inner orbit electrons are bound to the nucleus. The inner orbit electrons are bound to the nucleus. The inner orbit electrons are bound to the nucleus and the valency electrons are engaged in covalent bonding. The valency electrons are engaged in covalent bonding. Right, the valency electrons are engaged in covalent bonding. Thus, at this temperature, the covalent bonds are very strong. At this temperature, the covalent bonds are very strong. As a result, what would happen is there would be no free electrons. Hence, there are no free electrons. No free electrons. Right? There are no free electrons. Right? In terms of energy band, the valency band is completely filled and there is a large gap between the valency band and the conduction band. In terms of energy band, the valency band is completely filled. The valency band is completely filled and there is a large energy gap between the valency band and the conduction band. And there is a large energy gap. There is a large energy gap between the valency band and conduction band. There is a large energy gap between the valency band and the conduction band, right? The forbidden energy gap is sufficiently large to prevent any electron from the valency band to jump into the conduction band, right? Hence, at low temperature, no valency band electron can acquire sufficient energy to jump this energy gap and go into the conduction band, right? At low temperature, no electron in the valency band, no electron in the valency band has acquired sufficient energy, to jump across this energy gap, to jump across this energy gap and go into the conduction band. Right? Go into the conduction band. Due to this, semiconductors behave like perfect insulators at room temperature. Right? Due to this, semiconductors behave like insulators at perfect insulators at low temperatures. Fine, do we get this in clear? Now, at temperatures above absolute zero, this was A part. B part of this, at temperatures above absolute zero. Let's see what happens at temperatures above absolute zero. When the temperature is raised, some covalent bonds in the semiconductors break due to the thermal energy supplied. When the temperature is raised, some covalent bonds break due to the thermal energy supplied. Right, some covalent bonds break due to the thermal energy supplied. This sets some electrons free which are engaged in the formation of these bonds. This sets some electrons free which are engaged in the formation of these bonds. Right? As a result, at room temperature, when the covalent bond is broken, the electrons have acquired sufficient energy to jump the energy gap from the valency band to the conduction band. Right? So at room temperature, when the covalent bond is broken, as a result, at room temperature, when the covalent bond is broken, the electrons have acquired sufficient energy. The electrons have acquired sufficient energy to jump the energy gap from the valency band to the conduction band. To jump the energy gap from valency band to conduction band. Right? So the electrons would have jumped the energy gap from valency band to conduction band. Thus at room temperature, some electrons cross over to the conduction band, and which imparts a little conductivity to the semiconductor, right? And as the temperatures increase, more and more valency electrons cross over to the conduction band. As a result, the number of free electrons that are present in the conduction band goes on increasing, which then constitutes to a large current even at small potential difference. Fine, do we get this thing clear? So we said that they have acquired sufficient energy to jump from valency band to the conduction band, right? Thus at room temperature, some electrons which have crossed over to the conduction band impart little conductivity to the semiconductor. Some electrons which have jumped into the conduction band, impart a little conductivity to semiconductors. Right? Now as the temperatures increase, more and more valency electrons cross over into the conduction band. As the temperature increases, more and more valency electrons cross over to conduction band. More and more electrons cross over to the conduction band. As a result, there are a large number of free electrons now in the conduction band. As a result, there are large number of free electrons now in the conduction band. Right? Which help to constitute current. When potential difference is applied. So this is how you have the behavior of semiconductors at absolute zero and at room temperature. Next. Now what do we understand by holes? Concept of holes. Now in semiconductors, when an electron is dislodged due to the breaking of the covalent bond, it becomes a free electron, right? It moves from the valency band to the conduction band. It can wander and at random anywhere it wants in the conduction band, but in doing so, it leaves a space where it existed in the covalent bond. Now when it was in covalent bond, there was an empty space where it existed, right? There was an empty space where it existed. This empty space that is left behind by the electron, which has broken free from the covalent bond and has jumped from the valency band to the conduction band, is called as a hole. So hole is nothing but it is an empty space left behind in the crystal structure due to the breaking of the covalent bond, due to the electron jumping from the valency band to the conduction band, right? So do you understand what are holes? So I can say that in semiconductors, in semiconductors when an electron is dislodged due to the breaking of covalent bond. When an electron is dislodged due to the breaking of the covalent bond, it becomes a free electron. Right? Now, in the absence of that electron in the covalent bond, is represented as a small circle. The absence of the electron in the covalent bond is represented as a small circle. Right? It is represented as a small circle. This empty place or left behind in the crystal structure is called as hole. This empty space left behind in the crystal structure is called as hole. Fine, do you get this in clear? So thus, every time you get a free electron in a semiconductor, every free electron is associated with every hole. Fine, do you get this in clear? The free electron is formed due to the breaking of the covalent bond, and that empty space that is left behind due to the breaking of the covalent bond represents the hole. Fine, do you get this in clear? Next, what do we understand by intrinsic and extrinsic semiconductors? Right? What do we understand by intrinsic semiconductors? Now there are certain substances which have their resistivity between conductors and insulators. Such substances are called as semiconductors. Now, there are semiconductors. The most frequently used semiconductors in electronics are silicon and germanium. Right? This is because the energy required to break their covalent bond is very, very small. In the case of germanium, you require only 0.7 electron volts, whereas in the case of silicon, you require 1.1 electron volts. Right? Now, let us consider any one of these substances. Let's consider, say, germanium. Let's consider germanium in a crystal lattice. Right? Now, germanium has 32 electrons, and it has 2 electrons in the first orbit, 8 in the second orbit, 18 in the third orbit, and it has 4 electrons in its valency orbit. Now these 4 electrons are in the outermost orbit, or these are my valency shell electron. Right? Now in germanium crystal, each atom attracts the valency electron from other atom, and thus they share electrons, and that's how the covalent bond is formed, and that's how the valency of each atom is satisfied. Now as such, the covalent bond that is going to be formed between them is going to be extremely strong, due to which there is going to be no free electron. If there is going to be no free electron, if all the electrons are going to be tightly bound to the nucleus, then all the electrons will be there in the valency bond. As all electrons are in the valency bond, they will not have any free electron, and hence they will not be able to conduct electricity. See, I'll show you the structure of germanium. Let's see a crystal lattice of germanium. let's consider this is germanium atom, right? Now germanium atom has say 4 electrons. Let's show the 4 electrons, say with blue. Let's show these 4 electrons separately. So you have 1, 2, 3, 4. Each germanium has 4 electrons. Each germanium has 4 electrons. These are the 4 electrons in each germanium atom. Now they are going to form a covalent bond. The adjacent germanium atoms are going to form covalent bonds. So this is a covalent bond which is going to be formed here. This is a covalent bond that would be formed here. This is a covalent bond that would be formed here. This is a covalent bond. Covalent bond. Covalent bond. Covalent bond. Covalent bond. You would have covalent bonds formed between adjacent atoms, and as a result all the electrons are going to be used, right? All the electrons of germanium which have a valency of +4 are going to be used. As a result, at room temperature there is going to be no free electrons. All of them are going to be engaged in the formation of covalent bond. Covalent bonds are going to be extremely strong, hence there are going to be no free electrons available for the conduction of electric current. Such a semiconductor is going to behave like an insulator at room temperature, or at maximum it will offer very little conductivity at room temperature. Such a semiconductor is called as an intrinsic semiconductor. So what is an intrinsic semiconductor? A pure semiconductor is called as intrinsic semiconductor. Fine, do we get this thing here? Let's write this down. A semiconductor in an extremely pure form, a semiconductor in an extremely pure form, a semiconductor in an extremely pure form is known as intrinsic semiconductor. Right? Now, the covalent bond in intrinsic semiconductors are so strong that there are no free electrons available for conduction of electric current. The covalent bond, the covalent bonds in the intrinsic semiconductor are so strong. The covalent bonds in the intrinsic semiconductors are so strong that no free electrons are available. That no free electrons are available. No free electrons are available for conduction of electric current. Right? Therefore, an intrinsic semiconductor acts like a pure insulator at low temperature. Therefore, an intrinsic semiconductor acts like an insulator. An intrinsic semiconductor acts like an insulator at low temperatures. Fine, do we get this thing here? However, at room temperature, some electrons are produced due to the breaking of some covalent bonds by thermal energy. However, at room temperature, some free electrons are produced due to the breaking of some covalent bonds due to thermal energy. Right? Now these free electrons reach the conduction band and leave equal number of valencies, which are called as holes in the valency band. So thus in intrinsic semiconductors, the number of free electrons is always equal to the number of holes. Right? I can say that these free electrons reaching the conduction band, these free electrons reaching the conduction band leave equal number of holes, in the valency band. Right? Therefore, I can say that in an intrinsic semiconductor, the number of free electrons is equal to the number of holes. Now, when some external field is applied to an intrinsic semiconductor, the conduction through the semiconductor is with the help of free electrons as well as holes, but the number of free electrons are very few and hence a very small current flows through them. Right? So I can say that in the presence of external field, a small current flows through them. Small current flows through them as the number of electrons and holes are very few. Right? Do we get this in clear? Hence, a pure intrinsic semiconductor acts as an insulator at room temperature, or at the best, it acts like a weak conductor at room temperature. Right? Do we get this in clear? Next, what are extrinsic semiconductors? Right? What are extrinsic semiconductors? Now, at room temperature, intrinsic conductors offer very little current carrying capability. Hence, they cannot be used in electronic devices. In electronic devices, the material that is used should have proper conductivity. Now, the electrical conductivity of semiconductors can be greatly improved by adding some impurity during the process of crystallization. During the process of crystallization, if I add some impurity to a pure semiconductor, then the ability of the semiconductor to conduct electrons or the ability of the semiconductor to allow current will be greatly enhanced at room temperature. Such a semiconductor which has some impurity added to it is called as extrinsic semiconductor. This process of adding impurity during the process of crystallization is called as doping. Fine, do we get this thing clear? Doping is nothing but the process of adding impurity during the process of crystallization. Now, if I am going to dope the semiconductor, What are the different ways in which I can dope the semiconductor? I can dope the semiconductor either with a trivalent impurity or with a pentavalent impurity. I could dope the semiconductor with an atom whose valency is 3 or with an atom which has a valency of 5. If I dope the semiconductor with an atom whose valency is 3, then the number of holes will be greatly enhanced. Right? Since the number of holes will be greatly enhanced, such a semiconductor would be called as, it would have more number of holes, hence such a semiconductor would be called as a p-type semiconductor. If I dope the semiconductor, intrinsic semiconductor, with a pentavalent impurity, then each pentavalent impurity will give rise to one additional electron. Each pentavalent impurity will give rise to one additional conduction band electron. Hence, the number of conduction band electrons, the number of conduction band electrons would be greatly enhanced, right? Since the number of conduction band would be greatly enhanced, the flow of current would be due to these extra negative charges. Hence, such a semiconductor would be called as an n-type semiconductor. So let's see what are extrinsic semiconductors. I can say that the electrical conductivity of intrinsic semiconductors can be greatly increased to a great extent by adding some impurity in the process of crystallization. Fine. Now the added impurity is very small, right? Now this such a semiconductor in which some impurity is added is called as an impure semiconductor, or it is called as an extrinsic semiconductor. Such semiconductor is called as extrinsic semiconductor, right? And the process of adding impurity is called as doping. The process of adding impurity is called doping. Fine, do we get this thing clear? Now the doping material are called as impurities because they alter the structure of the pure semiconductor crystal, right? The doping material are called as impurities. The doping materials are called as impurities because they alter the structure of the pure semiconductor crystal, because they alter the structure of pure semiconductor crystal, right? These impurities are also called as doping agents. These impurities are called as doping agents. Fine. Now, the impurity atom can be of two types. Either it can be a pentavalent impurity or it can be a trivalent impurity. The impurity atom, the impurity atoms are of two types. One, pentavalent impurity, or second, trivalent impurity. Fine, do we get this thing here? So in pentavalent impurity, you would select an element that has valency 5. In trivalent impurity, you would select an element that has valency 3. In pentavalent impurity, you would select an element that has 5 electrons in its outermost orbit. In trivalent impurity, you would select an element that has 3 electrons in its outermost orbit. Depending upon the type of impurity used, you would get two different types of semiconductors. Either you would get a trivalent semiconductor, or either you would get a p-type semiconductor, or you would get an n-type semiconductor. Right? We'll stop this here for the day. Thank you very much.